flatten out all their work. And those indents are important. And that's whether on the on-campus, online, I saw that happening. People wanted to flatten that out. So I want to look at an if statement and really quickly. And so if, and then what we really are saying is if some condition is true. Then we're going to execute something, and it goes over to the right, and so we have a block of code. And so maybe that includes walk to campus, open door, enter classroom. So that condition that evaluates to true, and then we have an else. Stay in bed, sleep till noon. So we also tend to say end if. That way I know that that block of code has been completed. So when I enter this condition, so we're going to put in some condition here. And when that condition is true, so in this case, so if there is not a snow day, so as long as that condition evaluates to true. And notice the condition, though, has a not in it, and we have to do that a lot. So we have, if you want to think about it as a double negative, but I need to evaluate this condition. So if there is not a snow day, so if this sentence evaluates true, we execute these lines of code. Otherwise, we're going to execute those lines of code. So we can evaluate these in a lot of different ways, but if what I saw in a lot of people, they did this, I don't really have a clear idea which pieces of code are blocked out. And most programming languages use that blocked out, those indents, to say, all right, that's the line of code that's in that block. So in most languages, if we would not have those indented, that would end that if statement right there. It would just end on that open door, and then it would have an error and say, what is this else or these other pieces? In some cases, it doesn't even error out. It just doesn't work correctly. So when we start breaking out that logic, we need to look at, can we do that? So that blocking is the biggest piece I saw. You need to make sure that you evaluate those to some kind of a true statement. So this is the part that goes when it's true. This is when it's false. The other piece to make life easier, though, is we said we can put in conditions in here and we can combine them. And so we could combine that with an and we typically capitalize that so we can see it really easily. It's always a good idea to use parentheses so we can separate it. So maybe we have two conditions that both of those have to be true. So in this case, there has to be both not a snow day and in this case, work is canceled. But what we really need to say is work is not canceled. So in this case, if there is a snow day and work is canceled, this evaluates false, and we come down here. But if we had a snow day, but you still had work, so maybe you're working in the cafeteria, you would have to stay in bed. You wouldn't get to utilize that portion. So we can combine them. Now, the reality is what that evaluates to, or is very similar to, is if we had two if statements. But we can shortcut it and combine them, but we have to be able to evaluate both sides. And that's where those truth tables come in. So in this case, for a true, it has to be both parts of that have to be true for this to happen. If I had changed that to an or instead, then as long as either piece of that, so either work is canceled or there's a snow day, either one would do the same thing. We would end up with this being evaluated as true. So that's why we look at those truth tables and we look at this. So we can do the same thing though in Excel. So if you'll open up Excel, I want to show you how to do an if statement. Because I don't think we really get to that much in our 101 class. And it's kind of a handy way to do things. So I just randomly put a couple of values out here in column G. Doesn't matter where you put them. And I picked another cell out here. And I'm just going to type equals. And whenever I say equals, that says, hey, we're going into formulas. And I type the word if. And as soon as I type that parenthesis, it pops up and says, oh, okay. So if logical test, so that's what we're gonna do. We check to see if some value is true. And if it's true, we do this, else we do that. We don't have to have that else piece. It's an optional piece. And in fact, if you look at it, you can kind of see that. So my question here then is, if, and I'm just going to click on my value here, is greater than 100, comma, if I want to output text, I have to put it in quote marks. Put a quote mark in there. So it is the same thing as what we're doing, same logic. So I just put in there, if the value in G4 is greater than 100, comma, I put text in quote marks and text in quote marks. I can also output values. I can output another formula. I can do all different kinds of things. But this will show it very quickly. So in this case, smaller. There we go. All right. So in this case, my question was, is G4 greater than 100? Wait a minute. Why is it not giving me a true value? I'm saying is G4 greater than 100, right? So I'm asking, is 100 greater than 100? Which is false. If I said if it's equal to, so I can go in and change that, then I get my true response. Now, just out of curiosity, if I take all of that text out of there and I just have an if statement, let's see what happens. And it's going to say, oh, you have to have some piece in there. So I have to have so now it should say true. So I'm going to change this value and see what happens. Oh, wait a minute. I didn't type in the word false in there, did I? If I look at my, because we automatically will assume those Boolean values. And that true and false is what Excel outputs for that. But again, I can do all different kinds of things. So maybe what these are grades. And so maybe that is actually a 0.9. This one's a 0.8 because I may want to use it again. And so I can say if G4 is greater than a 0.9, then I want that grade to be an A. So I can do, I think I have maybe a period in there. I can't see on this monitor worth a darn. Chunk. All right. So it's not true. Why is that not true? I said if it's greater than, well, I need to probably set that to greater than or equals to, because now it'll include that 0.9. So I could sit there and use this to figure out a grade scale. Now, it gets a little more complicated because do we have more than one grade? We do. Well, we can nest in Excel the same way we're going to nest in other languages. We start at one end, and so notice inside of that where we would have a false value, I'm now going to put another if statement. So I could put in another if statement, and I could say if, I quit hitting the keyboard, so if chunk, and so I could nest those together and eventually end up with an entire set of those. So it gets a little chunky because we have all those nested inside of there. But on that else side, I'm nesting those together. And so I could then come out with a program that would put in a grade and output one really, really easy. So it's the same as saying in here. So this is a little easier to see because I know Excel doesn't blow up very big. So if G4, whatever value is that, is greater than or equal to 0.9, we're going to say then output A. And so then we have an else, and that else then has an if statement. So if G4 greater than or equal to 0.85, and so now we have to indent here output, and that would be that B plus. Else. And so then we would have another if statement here, and we would continue down that tree. So however many items we have, we would nest that far deep to get that. So it has to start at one end or the other. We could start at the F range and work our way up, but in this case we would hopefully pull it from the A's. So everybody that's in an A gets eliminated already. Then we look at the B's. Then we look at the C's, and we go down through the list. And so we nest those together to do that. So anytime we have a whole series like that, we end up doing that. So Notepad is our friend trying to look at those. And those if statements, how we ask questions, we have to sometimes do that where we have a question where we have more than one part. We want to ask multiple questions. Sometimes we have to nest them together. So think about our example of one of the games we had in the first couple weeks where we had rock, paper, scissors. And that's a really great example because we don't know what your opponent has. But what they have changes how we play and who wins. But it's three. It's got three different outputs. So we have to ask that question. So if opponent is equal to rock, we might lose. But we also have that else. And so the else would be either other possibilities. And so we would have to then ask if opponent equal paper, maybe we would lose again. Else, I'm going to indent that one out. So at that point, by asking 2 questions, we can get to the bottom of a 3 set. Because we can't directly ask, because our computer can only understand 1s and 0s, we can't ask a 3-part or 4-part or 5-point question. So we have to come back in and somehow be able to scrape through those. And we run into that a lot. We have questions. So we have a question of which grade do we assign to a score? How did you play in this game? So that's when we can do that. So here would be that else. Here now we win. And then we need, in this case, we're going to close this end if. And we need to close this one end if. So they have to match up. So we begin, we end. What can happen, though, if you don't indent or you start getting confused, is you end up with trying to close these and they're not nested together. They're trying to get outside of each other. So internally, that's the way this works the entire time. Now, we're going to show you some shortcuts, but the reality is that's how in some languages we have to do it. Other languages have some shortcuts that combine those. So this week we're going to start looking at the most powerful piece of programming, and that is that ability to loop. Everything else, if questions, well, the computer, we can ask those, but that doesn't make it any better than what we can do. We can ask questions, and in fact, we can interpret multiple answers. The computer can't. But what we are really bad at is doing things over and over and over again repeatedly. So the computer doesn't care if we make it add 1 plus 1 100 times. It doesn't care. On the other hand, if we had to do that, we'd get pretty tired of doing math problems. So we're going to look at loops and look at some of the ways we can control them. So you're going to see that that loop really is just some way that we can repeat an action. And we've done that. We've already had a little bit of a loop. So we had the while loop. So a while loop says, while something is true, we continue to loop. And we know that it's one of the issues is we know it's got to come back up here. So a lot of times we have to have that priming input. But because that loop will run forever, we also have to have one other piece. We have to have some way to change it. So if we want to have a loop that runs a defined number of times, so maybe we want to count to 100. We know that we have a defined number of times we're going to do something. So if we think about a sport of almost any kind, we have a defined number of things. So think about baseball. In baseball, we loop over and over again. We loop 9 innings. We could think of an inning as repeating. We repeat an inning, 9 innings. Now, we could hit a tie and have to end up playing more, but for the most part, we loop through things. So in this loop, we have to do a couple of things. We have to have a variable that we're testing. So often we call that the loop control variable. So in other words, this is the one that when it changes is going to allow us to exit that loop or test to see if we still need to be in that loop. So at some point in there we test that variable, and then at some point we have to get out of that loop. So here is one we'll take a look at. At the beginning of this loop, and here's what a lot of times we don't do, and it becomes a little bit of an issue. At the beginning of this loop, we declare this counter and we set its value to 0. So in this case, we say, all right, we have num, we're going to set count equal to 0. We've declared it's a number, and we have our test. It enters in the top of this loop. And so our test says, is that counter value we set up less than 4? Well, this first time through, yep, should be, and so it'll say hello. It then changes in this step. So we say count is equal to the value of count plus 1. So in other words, we're adding one number to it, one value, and shoving it back in and changing it. So at this point, we started at 0 on the first loop. Now we're up to 1, and it comes back up to the top of the loop. And we bring in 1. So is 1 less than 4? If it's true, then we output hello again. We add a value to it, so now we're at 2. We come back up to the top, and we do it again. So now we're at 3. Is 3 less than 4? Yeah. And we come down through here. But now we're at 4. Is 4 less than 4? No. And so once 4 says, oh, this equation is not true, I stop. So here's a question. How many times did hello get printed? How many times did we print hello in that scenario? So the way to do that is just work our way through that logic until we know what's going on. So did it print 4 times or did it print 5 times? Well, so we can go through that. So we know at 0 it prints once, right? So if we keep track on our hand or whatever else, it increases to 1. It prints at 1. It prints at 2. It prints at 3. Does it print at 4? Does it? So is 4 less than 4, so it's going to exit out. So in this case, it actually prints at 4 times. So the key to thinking about that is, how does a computer count differently than you? It counts from 0. When the computer starts counting, it always starts with 0. And we tend to think of it as 1. So there are ways we can make logical sense to us. So we can remember, all right, the computer counts at 0, and in fact, we forced it by starting at 0, didn't we? And we went to less than 4, so that may be just a remembrance. So 0 to less than 4 then is 4 times, 4 iterations. So could we change this to 1 and this to less than or equal 4? Because if I just changed this to 1, so it started counting at 1, this would only loop 3 times. I would also need to change this. So loops are one of those, how many times things are going to loop. And when we start getting into Python, you'll see that we run into that issue of, oh no, did that loop really run 4 times? Did it run 5? Did it run 712? Did it run 711? So the easiest way that I've found is just remember, if I want a definitive number of loops. We're also going to show you another shortcut when we start programming, but for now, I know that I'm going to start at 0, and if I say that this is less than the value I want to get to, I'm going to count from 0 to right up to that. So if I said I wanted 400 loops, and I said 0 here and less than 400, 399 would print. 400 when it gets here, so I've added 399 plus 1 to 400 is going to exit out. And so that's one just to kind of put in the brain and remember what's going to happen. So we don't have to always increase that loop. We can decrease that loop also. So same structure, we would just say, let me dump that out. We would just say count equals count minus 1. And remember that equal sign, what we're really saying is it's an assignment operator. So whatever's done on the right, that math operation gets done first, and then it shoves it to the left. So we can go up, we can go down. We don't have to go by ones. If you wanted to go down by tens for some reason, You could do that. We could go from 400 to... I'm not sure why you would do that, but there might be a valid reason for it. Maybe you're using that counter for some other value. So that loop control variable gives us a way that we can put a set number of times. So think about playing a game. Almost every video game, you get a set number of lives. In other words, you get a cycle through that entire game, a set number of lives. And so that's the same thing we're looking at here, is we're trying to come up with a way that we can count a specific number of times. So it has a value, and we can control how many values are in there. And in fact, I would say best programming practice would be, instead of writing this 4 in there, you would actually have a variable up here that you would call number of loops. And so you would actually say it's count less than number of loops. And that way, if I wanted to change that, so maybe this loop controls a game from the beginning, you could then change that. You could say, hey, you get a bonus. Now you get 6 turns instead of 4. So these loops, so we looked at a definitive or a definite loop, a number of set number pieces. So if we have an indefinite loop, then we have a loop that's going to run that we don't know how many times it's going to run. So we're relying on something maybe external to trigger it. So this might be more of an example of a thermostat. We don't want the thermostat to only run 10 times in a day and then just shut off. We'd like that thermostat to continually check for the temperature, and if the temperature is below a set point, then turn on the heat. So in this particular case, we're going to look at a loop that's got a value, and we tend to call those sentinel values. There's some other names, but sentinel means it's something we're monitoring. So we have a sentinel value. So in this particular case, we're going to have a loop. And so that loop is right here. And so it looks like that while loop. And so it says while response equals yes, output the bank balance is, and pull their bank balance. So bank balance equals bank balance plus bank balance times interest rate. And it says, do you want to see next year's balance? So if that's true, and they say yes, then you will output next year's bank balance. So in other words, you're adding the interest they would earn in a year to your existing bank balance and showing them what it is. So if I look at this loop here, this is what we're looking at. So they're going to say yes. As long as that response equals yes, this is going to loop continually. So you would be able to loop 20 years in the future if you wanted to of what your bank deposit is today. So whether this loop continues, we don't know how many times that could continue. It's dependent on this input of that response. But notice we also have to have that input response here. So this is our priming the input right here for our loop. This is the one that changes or can change to control that loop. So response controls whether that loop continues. We have to get a priming input. In other words, if we came in with no response, we wouldn't know whether we needed to continue or not. So you're going to ask that question of, do you want to see the bank balance? One more down. Up here, it comes into this loop, and then it can end at any point. So one of the ways we also do that, so a lot of times you'll see when we're coding, we'll put something in a loop and say, if you want to exit, type 999 or some number or value that you normally wouldn't see, and that will trigger it to exit out also. So Here we have this on a couple of programs, and they show what it's going to look like. So here's our beginning balance. We're starting at $1,000. Every time you say yes, it's going to add in this case, it looks like it must be 4% interest. Should be nice if your bank account could get that. So 1,000, 1,040, 1,081 because you have compound interest. And so you could go through as many times as you want to. So we have two ways to control that loop right now. So let's see if I can make this bigger, 5. So in this particular case, that loop, there's several different pieces we need to make sure we have in there. So that input response, so right up here, we have to initialize that variable. So here we're getting a response from them. So the customer has to say either yes or no. They're choosing whether to initiate that loop. If they say no, then it's going to exit out and say, "Yep, have a nice day." If they say yes, so while this loop control variable is still being tested, so while their response was a yes, then we're going to output their bank balance. Down here we're going to ask them again, and then we loop back up to the top. So what do we see as issues in here? Couple. If I don't have this priming input, that response, whatever that response is, I haven't initialized it. It's going to be some kind of garbage value. Most likely it's not going to be equal to yes. This program's going to go out, have a nice day. But I wanted to see my bank balance. Sorry, we exited. The other and bigger problem with this, what happens if I forget to put in this input down here? So I input it once, up at the top. So I did my priming. My program goes to run, and they say, "Yep, I want to find out what my bank balance would be next year." It outputs its bank balance, comes down through here. Do you want to see the bank balance? Oh, but I didn't get a response. What's going to happen? So I don't have this input. It comes back up and runs. And if I don't alter that, is that original yes ever going to change? And so we end up with what's called an infinite loop. So in other words, this program runs and runs and runs and runs and runs. There's no way for it to end. And we don't want that. We want to be able to get out of our loop. So loops can get a little more complicated. They can give us a lot of very powerful things. Does anybody in here use a clock? Okay. So a clock is a great idea of loops that we're going to control. So we've all seen the electronic clocks. And when the electronic clock goes from 0, it counts up and it hits 59, what happens next? It flips back over to 0, right? And it increments the next number over. So if we go from 10:01, 60 seconds go by, then we're at 10:02. So the best example I can think of as these loops is we have loops all the time we see around us, and the best example is clocks because they are independent from each other. So in this particular case, we have loops. And we're going to do a couple of loops, and we're going to put them over the top of each other. And so the best way I can describe this then is let's do one in Notebook or Notepad here so we can draw it out. So we know that certain things happen only so many times a day. So I'm going to say minutes is equal to 60. Seconds is equal to 60. Hour is equal to 24 in a day. And so I have those values up there. So I can use them and I can look at them. So in this case, I'm going to start with my seconds loop. So I'm going to say, I want to create a loop. So while second, oh, I need another variable. I should really use something. Well, I'm going to type second is less than second. So in other words, that really is the value of 60, and maybe it's easier to hard code it in here so you can see. So while second is less than 60, I'm going to output second. But I also then have to change that, because if I didn't create a change, there's nothing going to happen here. So I'm going to say output second, and so second equals second plus 1. So the other piece I need to do to start my loop is I need at the beginning, I need to set second equal to 0. And the reason I have to do that is a couple of reasons. We know we're going to loop this multiple times. I don't know what that value is. So housekeeping always says I should probably clean that out, because I don't know what value might have been stored in there previously. So now, imagine our clock. So our clock here is now looping around. So I'm going to end while. So here's a loop. It initializes a value. It loops, so while second is less than 60, so this should output the numbers 0 through 59, right? So magically our computer's really slow and it does it 1 per second. But I don't want just seconds. I would like to have minutes in here. And that minutes become that outer loop. So I'm going to come up here and I'm going to do a loop for minutes. So I'm going to say minute equals 0. So in other words, I'm starting with that counter. And then I'm going to say while minute less than minutes. So in other words, as long as our minutes are less than 60, so while that is true, here's where it gets really tricky. Notice how I'm indenting all these. All of this is going to run. So this entire loop is going to run 60 times, and I'm going to say minute equals minute plus 1. And then I'm going to end while. So for this program to run, it starts here at the beginning and it sets minutes equal to 0. And while minutes are less than minutes, in other words, while 0 is less than 60, so that's going to be true, and it's going to run this. Seconds equals 60, it's going to hit this loop. So this loop inside here is going to run 60 times. And when that 60 times are done, it's going to come out. It's going to end its loop, and it's going to add one more minute. And then our minutes are going to form their next loop. So internally here, this runs 60 times. This runs once. So if I just put a made-up counter in here, and so I just called it counter equals plus 1. And I set up here to the outside of that loop, I said counter equals 0. the end of this program, I put an output counter. What's the value on that output counter going to be? So if I work my way through this loop, we know that this runs 60 times, right? For every once this runs. How many times does this outside loop run? This whole loop, how many times is that going to run? So we start from 0, and we're going to get to 59 before it exits. So it's going to count on 59, and we'll go through. On 60, it's going to go, nope, because 60 is not less than 60. But since we count from 0 to 59, how many times is that? 60. So how many times is this little counter on the inside going to register? So this is going to run 60 times, this outside one. Every time this one runs once, this cycles 60 times inside, right? So that counter is going to get triggered how many times do you think? Is it going to say 60? So the first time, so let's do what we call that desk audit. Let's put numbers in and start working our way through. So we have minute equals 0. So I'll keep a little chart out here, maybe on the bottom. So I'm going to say min equals 0 right now. So we're coming through here. So while min equals 0, so 0 is less than 60, right? So we're going to run. We're going to reset seconds to 0. It's going to come down in this while loop. So 0 is less than 60, so this is going to run. So it's going to output a 0 for seconds. It's going to add 1, so seconds are now equal to 1. Counter is equal to counter plus 1, so this is going to go from 0 to 1. We're going to hit the end while, so it's going to come back up to the top of that while statement. It's going to come through here, so seconds are now 1. 1 is less than 60, so this is going to cycle through here 60 times. Once it hits 60 times, we are now equal to 59. Our seconds are equal to 59. That while loop ends. And it says, uh-oh. And so now this value is going to be equal to 1. It's going to add that 1 in there. And we're going to come up to the top of this loop and run this again. And so this is going to run another 60 times. So what I really end up with is the number of times this inside loop is going to run is equal to the number of times this loop runs times this loop. Or, so what's 60 times 60? That inside loop's going to run 60 times 60 times, which also happens to be the number of seconds in an hour. So if you ask Google how many seconds are in an hour, you're going to end up with 3,600. And it's going to run that many times. So our clock, though, so we have minutes, but we don't really output an hour yet, do we? So we could do the same thing. We could make this 3 layers deep. So we have hour. So hour equals 24 because we know that there's only 24 hours in a single day. So we did the minutes. Now we could do the hours, and we would do it exactly the same way. So we're going to say hour equals 0. So we're going to start our loop. And we're going to say then while hour less than hour, or in other words, while we're within 24 hours, we're going to create a loop. And so we would then move all of these pieces in. So now we're 3 layers deep on this, and we don't necessarily need that counter, but we might want it for something else. So this end while is at this layer. Okay, so while hour less, so I moved all of those pieces in. And so this is why that nesting and how those indents are very, very important. If we didn't have those indents, we wouldn't have a clue what's going on here. So this is the loop that does our seconds. This is the loop that does our minutes. And then this loop is going to be that loop that does our hours. So I'm going to delete everything down here temporarily. So we know if we begin a loop, we need an end for a loop. So we need an end while. Well, we also know that that loop would just run continually unless we changed it. So hour we set to 0 to start with, same as we did here. We need to then have at the end of this loop, so come down here, we have to have hour plus, or hour equals hour plus 1. So now if we ran this loop, if we ran this whole thing right now, we have a clock. It's going to display hours, it's going to display minutes, and it's going to display seconds. So all of those loops, so we have inside loops. Our furthest inside loop is the seconds. Our middle loop then is this, and our outer loop is our hours. So if I said, well, you know what, I want to know what counter is now. So this program completes one complete loop. So what is that counter going to be equal to? It completes an entire loop of 24 hours. What is a day, but that counter is going to display how many times this inside loop ran, or what it's really going to display is how many seconds were in a day, right? Well, and I don't remember what those are. But we know it would be, if I bring up the trusty calculator, we know that that inside loop runs 60 times for every time the minute loop runs, right? So 60 times 60, 3,600. We added 24 hours to that. So 86,000 seconds is what's going to be displayed if we ask that. So if we broke in and we said, how many times is this inside loop going to run right here in one day? 86,400 times. Your calculator or your clock is really busy trying to keep that up. So we have that idea of a calendar here, or a clock. So can it get even, could we add another loop? Yeah, could we add one for month or year or something? Yeah, we could do that. But we're already 3 layers deep, and I just wanted to show that that indent, this is how we keep track of that. Those whiles, notice all of them are at the same indent, and if we don't indent, you're going to look at that code and not have a clue what to do. Most programming languages, that's how they work, is by looking at that indent and saying, all right, I know that this is a block. It's indented from that while. So when that while loop runs, it's going to run every piece of that code inside of it. So loops are our friend. So there's problems with loops. A lot of problems with loops. And the problems tend to be us. So we don't alter that loop value. If we don't alter it, we can't get out of that loop in most cases. We may not use the right comparison, or we put loop statements inside that really should be outside, and when we get to those nested loops, you'll see that it's fairly easy to do. So here's an example of one where there's some incorrect logic. So here we come up and we say, all right, we have all these declarations. So there's a label and there's a string that says quit. So when you type ZZZ, that program sees that as a Sentinel value and says, oh, I'm gonna quit. So in theory, we get this value here and it's going to quit, right? And stop. But does it ever ask for that value? And the only way in this program's case that it quits is if it sees ZZZ. So what it's going to do is run through this loop continually. So it's going to never stop. Because we're never going to have the chance to input, are we going to quit? So, we also have a couple of other issues with this one. So, no value is input for that name. So we never get a value at the beginning. We don't initialize this label counter. So label counter is a value we use in here. We don't know unless we initialize it and say specifically, this value we set to 0 at the beginning of that loop. This program could have run 4 or 5 other times. There could be a value in there already. And when we just create a variable, we don't always know where it's being assigned. All our computer is, if you think about it as a set of buckets, and we've said, I want to get a value that's stored in this bucket. Unless we clean it out, we don't know that. So there are a lot of ways that we can make mistakes with these. So here we do take an input, so same program. We take an input for a name. Well, okay, that's good. And we could escape that way, because if they don't want to ever run that program, they could do it. I have another problem. Well, okay, we don't take a new name, but so here we say, all right, so we're going to input production. We're going to have a label counter equals 0. Okay. And then label counter is equal to production. Okay. So if that's true, then we exit. Otherwise, we come over here and we output the label text. And we loop over and over and over again. But we never change that label counter. So we did it correctly at the beginning. We set it equal to 0. But we don't have any way to check it. It's never going to increase or decrease. So whatever that initial value is, in this case of 0, it's always going to be 0. Which means our loop here is always, this one here on label counter, is always going to evaluate false. And so we're just going to sit there and output labels until the machine runs out of paper or labels or supplies or whatever it is. So creating these loops and making sure that we have a way out of them is critical. Anybody in here drive a General Motors car? A General Motors car. General Motors actually had some programming done on their brakes that was wrong. And what they discovered when they checked it was you could get into a loop where your brakes would not lock up. So you could push down as hard as you wanted, the anti-lock brake would fight you. And it was because they had some loops set up wrong. It never changed that value correctly, and suddenly your brakes aren't going to work. So, here we have 2 loops, and we want to output hello 10 times. So, in this case, we have the example on the left. So we set our counter equal to 0. We want to do 10 loops. That's all we want to do is 10 loops. So we want to set the name hello 10 times. Maybe we're printing badges with it. Who knows what. We just know we want to set it to 10 times. On the left, if we count through, that actually works. On the right, because we said less than or equal to 10, it's going to actually print 11 times. And you can run the desk audit and go through and figure out why. But the reality is, because we can't started counting at 0, so it's going to print when the counter is equal to 0, and it's going to print when the counter is equal to 10. And that's 11 spots between 0 and 10. So there's a couple ways we could fix that. So the easy way is take out the equal sign. But maybe I'm using that counter value and I'm counting these badges and I'm printing that on the badge. The other way I could do that then, if I really wanted that value set to what we needed, so maybe we have a statement in there that's printing out a value. So you're printing 1st through 10th place. The easy way I could fix that then is if I change that counter and I set it to 1, that would give me the same number. That would give me 10 sets. So same output, different ways to set up the input. So in this case, there's a couple of different ways we can do it. All right, so this particular program, this one says, all right, here's a program that's going to calculate, and it's going to do a lot of different calculations. So here it says, if we look at our declarations, we have hourly pay, weekly pay, hours per week, per percent, raise, start percenting, end percents, change percent. So we have a lot of different variables up there. So first step says, all right, output says enter the employer's pay rate. And we input an hourly pay. So we put $10 in. Whatever that happens to work out to. So we output enter the hours worked. Then we input a value. So here we want to say percent equals start percent. So percent up top equals start percent, or 0.005. And so then our percent, we go down into our loop. So our loop is based on that value percent. Is percent less than or equal to ending percent? So we go back up. Ending percent is 0.1. Is 0.05 or 0.005 less than 0.1? Yup. So we're going to run through this loop. And that loop says weekly pay equals hourly pay times hours per week. Oh. So we calculate what they make a week. And then we say a raise equals weekly pay times percent. Output percent pay raise. And then it changes percent equals percent plus change percent. So in other words, what we're outputting then is their weekly pay, what it would be on a raise. So you could look at that raise of different percentage levels. So you're doing kind of a what-if analysis. But one of the things that's really silly in here, does their weekly pay ever change? Do we need to have it in that loop every time? So if it's a value that doesn't change, why are we forcing that computer to calculate it every time? So if we moved it up and said, all right, we're going to calculate it up top, we can still get that value, and we don't make the computer or whoever it is calculate that every single time. If it's something that needs to change in there, then we could move it down. But a lot of times we do that. We don't think through where items are. And so in this case, this would be far better to be tucked up here. And it would allow you to say, here's our hours, bump, bump, bump. And then we just access that. We don't need it down here. We use it here in weekly pay, but we don't need to recalculate it every time. Now, if we were changing that, so their weekly pay was different for some reason, then we would have to look at that. But in this case, we're only calculating a raise, and we output that percent raise as both a number and a percentage is what we're doing. So in this case, it doesn't look like you're changing a lot of things by doing that, but think about a payroll at a large corporation. They have 1,000 employees. And now every loop that goes through there, you've got additional processing. It may mean the difference between a hour-long payroll cycle and a 5-hour payroll cycle to complete. And those simple mistakes or simple issues in there add up over time. And we think of our programs running really, really quickly. But I work with some organizations that do things like payroll and bills. And so the amount of time, for example, on a system we're working with, it outputs all the bills for a small city, about 4,000 customers. And the processing to calculate those bills, because they have done some changes in the way they process it, we went from a small, slow machine to a faster machine, updated the software, and it went from an hour to process to 5 to 7 hours now to process. And it's because they've included things in there, and they're forcing that computer to do things repeatedly that we really don't need to do. All right, on Thursday we're going to talk about for loops. We're going to go over the homework for last week. And if you look at the homework for this week, let me bring it into the screen. So this week, your homework is another debugging exercise and some multiple choice questions out of the book. And so we will look at these common errors and see if any of those jump out at you when we look at that homework. All right, there is going to be a discussion board this week after Thursday. So one of the things we're going to start doing in a lot of cases is your homework and assignments, once they're turned in and done, and we don't want to turn them in ahead of time so somebody else can freeload off your work, but we want to be able to start displaying your efforts, and that way maybe you can see what other people are doing, and that can give you some additional guidance in how we can get there. So we only have a couple of weeks, and then we're actually going to be in Python. So one of the things I would like to do is also really quickly is take a look at Python. And so I know we're a couple weeks out, but I want to make sure that we can install it. So the place to go for all things Python is python.org. So there's a lot of different reasons we use Python in here. It's free. It's really English language looking. It looks a lot like this pseudocode we're working with. And if you can break a problem down in pseudocode, you can probably break it down in Python. So what we are going to do is look at this Python site really quickly. So there's a couple of different areas. There's community, and you'll notice there's all different kinds of pieces in there. Stories about people using it, news, events. You can actually find downloads. You can find every piece of help about Python you can ever want. So notice all there's documents. And in fact, if I want to say, hey, I really like Python, I want to find a job, there are right now currently 159 jobs listed just on this website alone. Now, some of these are obviously outside the United States, but who wouldn't want to go to Ireland and work? So you'll notice that it gets used by a lot of different companies. And so this can kind of give you an idea of some of those companies that use Python or some derivatives of Python. So one of the interesting ones I did last summer was I took a class. You're really, I took a class at Southeast Community, or not Southeast, at Iowa Western. They have a summer program, and I actually got to work with a couple of engineers from Google. Google uses Python extensively. They can't tell you what and all they do with it, but they use it as a really quick scripting language so they can monitor and manage their system. So you'll see it a lot of places that it's being used for. But the first thing we need to do is we need to get it installed. So if you look under Downloads and you click on Downloads, you'll notice that there are a huge number of versions. So you can get all different kinds of versions. You can get it for, if I scroll down a little bit, because it automatically says, all right, here's Python for Windows, because I'm on a Windows machine. You can get it for if you have a Mac. There's a version that floats right on a Mac. If I want Linux, there's versions that will work on Linux. You can put it on tablets. You can put it on your phone if you really want to. There are Python languages. Probably the phone is not the best way to do it. But the weird thing is, you notice there's two different versions. There's a 3.6 and a 2.7. So the software hit a split. And so some of the ways we do things in the older versions, the 2.7, is different than the way we do in the 3.6. So the two versions are different than the 3. And we want to look at the latest version, but they still offer the old version because there's a ton of software out there already written in it. So all I'm going to do is I'm going to click download, and you'll see this is about a 10-second download in here. So very small program. I'm going to run it, and I'm going to say, yep, I want to install now. It's probably going to pop up my little bubble in here and say, yes, I do need a user. So now it's going to go in and install. Doesn't take very long at all. And so this is the environment we're going to be working in fairly quickly. Another 5 seconds maybe. So it is installed in here in the lab, but if you're working anywhere else, you'll need to install it. Installing license. Let me show you what it looks like when it's done. So the Mac version does look slightly different, it appears, but all the same functionality is there. All right, so one of the things that you can certainly do to kind of prep and start looking at this is they've actually got an online tutorial. And we'll look at it again, but here is the online tutorial of anything you can ever ask about Python. So if I want to look at what the Python interpreter looks like, so everything we could need is here. I'm going to close this. And then if I go look for Python and I just start typing Python, it's going to pop up the interpreter, but what we normally want, you'll have to go to All Apps. And what we like is this idle. So it's an environment that's going to look a little different. So the one you want to be able to open is this. You want to be able to open this version. And so it's under idle, IDLE. And that is where we are going to take off from in the next couple of weeks. That is Python. Doesn't look scary at all. And so we'll be able to file and save, and we'll work with that extensively. So to make sure that everybody gets that installed, I'm going to go ahead and leave this on the video. Go ahead and install it on whatever device you're going to do homework on. Make sure that you can install it. I have not had a ton of difficulties installing this on nearly anything. There are versions of it that will float out for almost anything. And then if you want to test it, notice what I did there is I did a print statement. I said print, and because it's a function, like all functions in math or anything else, I enclosed it in parenthesis so it's that easy to use. Nothing complicated yet. It is sensitive to some things though, so when I talk about making sure we do lowercase and uppercase, notice what happens if I do print there are some weird syntax issues to worry about when you get there and to be aware of. So print has to be lowercase. All of our functions tend to be lowercase. So that is Python. Make sure you get it installed. Thursday we'll go through a ton of more loops. We'll do a for loops and some other pieces. So.